Alright guys, here we go with a one-dimensional interference example. The problem says two loudspeakers emit sound waves along the x-axis. A listener in front of both speakers hears a maximum sound intensity when speaker 2 is at the origin and speaker 1 is at x equals 0.5 meters. If speaker 1 is slowly moved forward, the sound intensity decreases, reaching a minimum when speaker 1 is at x equals 0.7 meters. Part A says what is the frequency of the sound, and Part B says what is the phase difference between the two speakers. And this means the initial phase difference. What is the initial phase difference between the two speakers? All right, so let's go ahead and start with a sketch. And this describes two situations here. First, when speaker 1 is at 0.5 meters, and the second, when speaker 1 is at 0.7 meters. And so I'm going to call this situation A and situation B. So starting with A, we have a speaker number 2, which is at the origin, and we have speaker 1, which is a distance 0.5 meters away. And I'm going to call this distance here delta XA, because it's the distance between the sources in situation A. And we're told here that in this situation that the sound is at a maximum intensity. So that means that we get constructive interference when these two waves overlap, and in other words, that the phase difference for situation A must be equal to some multiple of 2 pi. All right, so our general expression for the phase difference between two interfering waves is 2 pi over lambda times the distance between the sources, the path length difference, plus the difference in the initial phase between the sources. And in our case, in situation A, that needs to be some multiple of 2 pi because we have constructive interference. Okay, so we can rewrite this expression just that the change in the phase, or the difference in the phase between the two waves in situation A is 2 pi over lambda times the path length difference, delta XA, plus the difference in the initial phase between the waves, and that must be a multiple of 2 pi. All right, let's move on to situation B. And in situation B, we still have speaker 2 at the origin, but now speaker 1 is further away at a distance of 0.9 meters. And we're told that the sound intensity decreases, reaching a minimum when speaker 1 is at this value of 0.9 meters. This problem says 0.7 meters, and this is wrong. It is 0.90 meters. I have an old printout here. So in situation B, the separation distance is 0.9 meters. And we're told that that's destructive interference, so we're going to have that the phase difference between the two waves, the wave produced by speaker 1 and speaker 2 in situation B, must be m plus a half times 2 pi, or in other words, an odd multiple of pi, 1, 3, 5, etc. And I'm using the same letter m here because we're told that the speaker is moved continuously from position A to position B, and that the sound goes from a maximum to a minimum. So we know that there's not any maxima or minima in between situation A and situation B. So that means that our index m must be the same for those two situations, right? We go from some multiple of 2 pi, and then we go to the very next odd multiple after that in this situation B. So we can repeat this process of writing down the total phase difference between the waves as being equal to 2 pi over lambda times the the path length difference between the waves, which is 0.9 meters, plus the initial phase difference between the waves, and that must be equal to some odd multiple of pi. All right, so now we have two equations here, and we have two unknowns. We don't know what lambda is, and we don't know what the difference in the initial phase is. And so let's go ahead. Part A asks for the frequency of the sound, so let's solve for lambda first. And I'm going to get at that by subtracting these two equations. That's going to go ahead and cancel out our m's, and it's also going to cancel out our initial phase constant phi 0. So let's go ahead and take equation B minus equation A. Okay, so on the left-hand side, that's going to give us 2 pi over lambda times the path length difference in situation B minus the path length difference in situation A. Okay, the initial phase constants are going to cancel. And on the right-hand side, we had m times 2 pi minus m plus a half times 2 pi. So that's just going to leave us with a pi. Okay, now we're in a position to solve for lambda because it's the only thing we don't know here. So we can go ahead and cancel the pi's and bring the lambda over to the other side. And we're going to get that lambda is equal to twice the difference in the path length in B minus the difference in the path length in situation A. Okay, the difference in the path length in situation B was 0.9 meters. In situation A, it was 0.5 meters. So that's going to give us that lambda is equal to 0.9 minus 0.5, so that's 2 times 0.4. Or in other words, lambda is equal to 0.8 meters. Okay, it asks for the frequency, so now we just need to apply the velocity relationship. Velocity is equal to the wavelength times the frequency, or the frequency is equal to the velocity divided by the wavelength, which is equal to the velocity, the speed of sound, 343 meters per second, divided by lambda, which is 0.8 meters, which gives us a frequency of 430 hertz. So there we are for part A. Now for part B, we need to find the initial phase, and we can use either one of these equations, either the equation from situation A or the equation from situation B. I'm going to use the equation from situation A, and this is for part B of the problem. And so we have, returning to that original expression, the phase difference between the two waves is equal to 2 pi over lambda times the path length difference between the sources, here in situation A, plus the initial phase difference between the two sources, and that must be equal to some multiple of 2 pi. Now we're going to calculate the initial phase difference here, and we always report initial phase angles as some value between 0 and 2 pi. So I'm going to take m equals 1 because we want just the first occurrence of this. Now the initial phase angle could be any multiple of 2 pi after that, but that doesn't really add anything to our picture here. So we're going to take m equals 1, and that's going to give us that the initial phase difference between the two sources is equal to 2 pi minus 2 pi over lambda times the path length difference between the two sources, delta xa. What's left is to plug in some numbers, and so we get that the initial phase constant, or the phase difference between the two waves initially, is delta phi 0 is equal to 2 pi minus 2 pi times delta xa, which is 0.5 meters, divided by lambda, which we calculated to be 0.8 meters. Okay, let's look at this piece for a minute. 0.5 meters divided by 0.8 meters is the same as 5/8, just an ordinary fraction. And we can multiply through by 2, so 5/8 times 2 is 10/8, so this is going to be 10 pi over 8, which can be simplified to 5 pi over 4. And so our initial phase constant is 2 pi minus 5 pi over 4. So 2 pi is the same as 8 pi over 4. 8 pi over 4 minus 5 pi over 4 gives us 3 pi over 4 left. So we get that the initial phase constant between the two waves is equal to 3 pi divided by 4.